Hello everyone. In this lecture, we are going to discuss about the inductance of a composite conductor. Okay. In the last class, we have discussed about the inductance of single conductor. Now here, we are going to discuss about a inductance of composite conductor. The now the objectives of this lecture are the first one is we need after completion of this lecture we are able to calculate flux linkages calculation of a one conductor in a group of conductors. The second objective of this lecture is calculate inductance of a composite conductor. And third objective of this lecture is concept of GMD and GMR. Okay, so now before going to calculate the inductance of the transmission line, first we need to calculate the flux linkage of a flux linkages of a one conductor in a group of conductors. So for this, I am considering a group of conductors V, that conductor 1, conductor 2, conductor 3, so on, conductor N. Okay, the group of conductor consisting of conductor 1, conductor 2, conductor 3, so on, conductor N respectively. Okay, let I am assuming further that I1 be assumed as current flowing through the conductor 1, I2 be assumed as current flowing through the conductor 2, and I3 be assumed as current flowing through this conductor 3, so on, In be assumed as a current flowing through the conductor N. Now, suppose I am assuming the conductor, I am assuming a remote location point P. So, that I am assume I need to calculate the flux linkages of one conductor in a group of these conductors up to the remote location point P. Okay. For this, again, I am considering the distance between conductor 1 and conductor P is from here to here. The distance between conductor 1 and conductor P be assumed as D1P. Similarly, distance between conductor 1 and conductor P is assumed as D2P. Similarly, distance between conductor 3 and conductor P is assumed as D3P. Similarly, distance between conductor N and conductor P is assumed as D and P. So these are the distances assumed from each conductor to the conductor remote location point P. Now we need to calculate the flux linkages of one conductor. Suppose I need to calculate the flux linkages of conductor 1. So the flux linkages of conductor 1 is due to not only the current flowing through the conductor 1, that is I1, the flux linkages of conductor 1 is due to all the currents in this individual conductors. Now first I have to assume the flux linkage of conductor 1 due to its own current. Flux linkages of conductor 1 due to its own conductor current I1. Okay, due to its own conductor current I1 is given as up to this remote location point P is given as lambda 1P of 1, which is equivalent to 2 into 10 power minus 7 into I1, that is current flowing through this conductor 1, I1 into logarithm of D1P by D11 where D1P is the distance between conductor 1 and P, D11 is the distance between the conductor 1 to 1 itself, self distance. Okay. Similarly, flux linkage. Okay. Similarly, flux linkage of conductor 1 up to this point P due to the current in conductor 2, that is I2, is given as 2 into 10 power minus 7 into I2 into logarithm of D2P by D12. Okay, the distance between conductor 1 and conductor 2. Similarly, we will find out the distance between conductor 1 due to the current in conductor N is given as lambda 1Pn equivalent to 2 into 10 power minus 7 into In into logarithm of dnp by d1n. Now, these are the flux linkages of conductor 1 due to the each conductor current I1, I2, I3, so on, In. So now the total flux linkages of conductor 1 is given as lambda 1p, which is equivalent to sum of lambda 1p1, it is due to current 1, conductor current 1, plus lambda 1p2 plus so on lambda 1p. Okay. So we have to substitute these values of lambda 1p from this equation, lambda 1p from this equation, and lambda 1p from this equation. We solve this equation 2 into 10 power minus 7 is common factor. Okay. Now the value of total flux linkages of conductor 1 up to this point P will be taken as 2 into 10 power minus 7 into I1 into logarithm of d1p by d11 plus I2 into logarithm of d2p by d12 plus so on logarithm of dnp by d1n. Okay. Now in this equation, each and in logarithm term there is denominator term and denominator term. I have splitting these terms. So the d1p will written as 2 into 10 power minus 7 into I1 into logarithm of 1 by d11. First I have wrote the denominator terms. Okay. Now I2 into logarithm of 1 by d12 plus so on logarithm of 1 by d1n. Okay, plus 2 into 10 power minus 7 into I1 into logarithm of, now I have writing the denominator terms, d1p plus I2 into logarithm of d2p plus so on in, in into logarithm of dnp. Okay. If you observe this diagrams, D1P, D2P, D3P, so on, DNP are the distances of each conductor 1, 2, 3 respectively P. As this point P approaches to infinity, all these distances are identical equivalent. That is, as P approaches to infinity, D1P is approximately equivalent to D2P is approximately equivalent to DNP. Okay, so on D3P, so is approximately so on all the distances DNP. I am assumed as a D. Okay, small d equivalent to D. So if you substitute in D1P, D2P, and D all these values as D in this expression. Okay, so this second term will happen 2 into 10 power minus 7 into into here logarithm of d, I1 into logarithm of d, I2 into logarithm of d, so on, In into logarithm of d. So I have taken logarithm of d as common factor into I1 plus I2 plus I3 plus so on IN equivalent IN. Okay. So now we know that sum of this current is equivalent to 0. So the entire second term is vanishes. Okay, entire second term is vanishes. Therefore, lambda 1p which is equivalent to 2 into 10 power minus 7. So this term is entire vanishes. So secondly, the left term is only this one. So 2 into 10 power minus 1 into I1 into logarithm of D11 plus I2 into logarithm of 1 by D12 plus so on In into logarithm of 1 by D19. Okay, that will be taken as equation number 1. Okay, I'm assuming this is the equation we are using to calculate the flux linkage of one conductor which is existing in a n group of conductors. Okay, lambda 1p is equal to 2 into 10 power minus 1 into I1 into logarithm of 1 by d1 plus I2 into logarithm of 1 by d12 plus so on In into logarithm of 1 by d1n. We can represent this value as in generalize that equation. Okay, generally we can write this equation as lambda I. Suppose I have to find, I want to find out, okay, flux linkage of, in generalize we need to write the flux linkages of conductor I. Okay, flux linkages of conductor I can be written as lambda I equivalent to 2 into 10 power minus 7 into sigma II into logarithm of 1 by d ij. Okay, ij into logarithm of 1 by d ij, where j equivalent to 1 to n. Okay. So this is the generalized formula we have to use to determine the flux linkages of any conductor. Lambda equivalent to, so from this equation we can recognize in generalized form as this one, lambda equivalent to 2 into 10 power minus 7 into sigma ij into logarithm of 1 by d ij. Okay, where j is equal to 1 to n conductors. Okay, I hope you understand this concept, flux linkages of one conductor in a group of n conductors. Now we are moving to discuss about the next one, that is inductance of composite conductors. Inductance of composite conductors. Okay, inductance of composite conductors. Okay, so for this I am assuming two conductors, conductor A and conductor B. Okay, the composite conductors means conductor consisting of more number of subconductors. So let me take in two composite conductors respectively A and B respectively. So here conductor A having a subconductors of 1, subconductors of X subconductors enabling conductor 1, conductor 2, so on conductor X. At I assume X conductors are existing in a conductor A. Similarly, Y conductors are consisting in a composite conductor B, which are labeled as 1 dash, 2 dash, so on Y. Okay, so I am assuming the current in conductor B assumed as plus I be the total current flowing in this composite conductor, whereas current flowing in this composite conductor will be IB in such a way that is this is the IA value and this is the IB value. Okay, so in such a way that IA plus IB equivalent to 0. That is, one conductor A acts as a go conductor, and conductor will be taken as the return conductor. One is acts as a go conductor, live conductor, and another one is act as a return conductor. So for this, I am assuming further each and every conductors of this case, each and every conductors of this value is assumed as a identical. Okay, here X groups are conductor, so each conductor, okay, each conductors of that we assume strands. Okay, each strands of conductor A carries I by X. I assume that each and every conductor of each or individual strand of conductor A carries equal current. So total I by total number of currents Ix. Similarly, each strand of conductor B carries minus I by Y amount of conductor. Okay, total current of conductor B is minus I. So total number of strands in a conductor B is Y. So each strand current carries a minus I by Y. Okay. Let I'm assuming further. So the flux linkage of, I need to calculate the flux linkage of conductor 1. Okay, strand 1 of conductor A. Okay. Now I have to finding the flux linkage of strand 1 in conductor A, okay, which can be written as lambda 1 equivalent to, you know that from this previous expression. Okay, I am using lambda 1, and here J equal to 1 to X plus Y, total X number of conductors X and X number of conductor Y. So here in this, all currents of conductor A carries same amount of current. So I have taken 2 into 10 power minus 7 into all conductors, all strands of conductor A carries Ix. So I have taken current is also taken as common factor. Now logarithm of distance between each and every conductor is 1 by d11 plus logarithm of 1 by d12 plus so on logarithm of 1 by d1x. Okay, plus there are the flux linkage of conductor 1 due to the strands of conductor B also. Okay, but these all these strands of conductor B carries a minus I by Y. So I have taken this value. Otherwise, I have taken minus 2 into 10 power minus 7 into I by Y into logarithm of 1 by d11 dash plus logarithm of 1 by d12 dash plus so logarithm of 1 by d1y. Okay, this is the flux linkage of conductor 1 due to the currents carrying in all strands of conductor A as well as all strands of conductor B. So if you observe this equation, that is lambda 1. So if you observe in this equation, this one is in the form of log A plus log B, in this bracket log A plus log B plus so on log B. So you can write as simplification log A plus log B as log AB. Okay. Now here this 10 can be written as lambda 1 equal to 2 into 10 power minus 7 into I. Okay. This both the terms 2 into 10 power minus 7 into I can be taken as common factor. Now this 1 by x can be taken as this 10 into 1 by x into logarithm of, again here this one is log A plus log B notation. So I have to use this function logarithm of d11 is 1 by d11 into d12 into so on d1n. Okay, minus, so next time is here minus 1 by y into this factor. So minus 1 by y into logarithm of, again the same concept, log a plus log b notation. So resultant I can write here 1 by d11 dash into d12 dash into so on d1y. Okay, this is the lambda 1, it is flux linkages of strand 1. Now we can simplify this value as lambda 1 equivalent to 2 into 10 power minus 7 into I into here 1 by x. Okay, we can return the a x log a can be written as logarithm of a power x. So here I am using this factor, but here 1 by x term is there. So logarithm of 1 by x can be written as logarithm of 1 root a. Okay, so I am using this concept here. This 1 by x can be shifted into the logarithm. So here logarithm of 1 by root of x root of, so here x value is there. So x root of d11 into d12 into so on d1n, so on d1n. Similarly here also we can write minus logarithm of 1 by y can shifted into this logarithm, it is y root, becomes y root. So 1 by y root of d11 dash into d12 dash into so on d1y. Okay, now we can simplify this equation for further. That is here log a minus log b notation, it is log a by b. So the resultant value will becomes, this will becomes into the denominator value, that is y root of logarithm of y root of d11 dash into d12 dash into so on d1y divided by x root of d11 into d12 into so on d1n. Okay, this is the resultant value of flux linkage of one strand, that is strand 1 of conductor A. Now we will calculate the, similarly we can, this is the lambda 1. Okay, now we can calculate inductance. Now we can calculate inductance of strand 1. Inductance of strand 1 is calculated as, you know that L1 equal to this ratio of flux linkage of strand 1 by current flowing through the strand 1, right? This is lambda 1 by I1. I1 is the current to the strand 1. As you know that current to strand 1 is I by x. So if you substitute the lambda 1, here I and I gets cancelled. So here x term will be converted into the numerator term. So this equation becomes 2 into 10 power minus 7 into x into logarithm of y root of d11 dash into d12 dash into so on d1y divided by x root of d11 into d12 so on d1x. Sorry, here x. Here is x d1x. Okay, this is the equation of inductor 1. Similarly, we will get the, this is the inductance of strand 1. Similarly, if we derive the inductance for strand 2, we will get the L2 equivalent to 2 into 10 power minus 7 into x into logarithm of y through tau will get d21 dash into d22 dash into so on d2y divided by x through tau d21 into d22 into so on d2x. Okay, we can obtain the inductances of each and every strand. Okay, now we will find the total inductance. Okay, as you know that if you observe here, this is the inductance of strand 1 and this is the inductance of strand 2. So if you observe here, both the inductances of two strands are different. So if you calculate for all strands of conductor A, all the strands will having a different inductances. Okay. Now I have to take in the, for this I have taken the average inductance. Okay, average inductance of strands of conductor A is taken as L average equivalent to sum of the strand Lx, L1, L2, so on Lx by x number of strands. Okay, this is the L average. So therefore, such x strands are connected electrically in parallel. X strands connected electrically in parallel electrically, right? Therefore, inductance of conductor A is, that is LA, inductance of conductor A equivalent to L average by x. Okay, L average by x, that is equivalent to L1, already L average is equal to L1 plus L2 plus so on Lx by x divided by x, we get the x by x into x. So resultant is L1 plus L2 plus so on Lx by, already it is here x, by x we get the x into x, we get the x square. This is the inductance of conductor A. Okay. For example, x, if you know that, okay, I am using this formula how it is. This is some n conductors are connected in parallel. For example, 4 conductors are connected in parallel. So each conductor having the same inductance L, 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 L. So what is the resultant? Since 4 inductors are connected in parallel, but all are having equal value. What is the equivalent value? L equivalent equal to L by 4, right? So here, now I am assuming L. I am assuming each and every conductor of this X strands will be assumed as L average. So L average by total number of conductors here is X. That's why I am using L average by X. Okay, now this is the inductance of conductor A. Okay, L1 plus L2. Now substitute the L1 plus L2 from this previous derivation. This is L1 and this is L2. From these two terms, 2 into 10 power minus 7 into x is taken as a common factor. So now LA, which is equivalent to 2 into 10 power minus 7 into x. Already here denominator 1 by x is there, 1 by x square is there. Okay, I have taken first 1 by x square into L1 plus L2. In this all those cases, 2 into 10 power minus 7 into x is common. So first L1 is, here what we written is L1 2 into 10 power minus into x into logarithm of this term. This is logarithm of y through tau d11 dash into d12 dash into so on d19, so d11 by x through tau d11 into d12 into so on d1x. Okay, this is L1. Similarly for L2, so on. For Ln, we will get the logarithm of y through. Similarly, we will get for ln into y through for conductor x dx1 dash into dx2 dash into so on dxy, okay, divided by x root of dx1 into dx2 into so on dxx. Okay, so this is the inductance of conductor A. Okay, if you observe here case, here log A plus log B notation is there, so we can simplify this equation. Here again, here 1 by x square into 1x and 1x gets cancel each other. Okay. Here denominator 1 by x square is there, so 1x, here 1x is cancel each other, so it resultant 1 by x is there. So this term can be written as LA equivalent to 2 into 10 power minus 7 into 1 by x into logarithm of, if you observe here, this one is in the form of log A plus log B. Okay, log A plus log B can have log AB, that is y root is common. So y root of d11 dash into d12 dash into so on d1 y, so on products into dx1 dash into dx2 dash into so on dxy. This is the numerator term, and now the denominator term is x root of d11 into d12 into so on d1x, so on dx1 into dx2 into so on dxx. Okay, now here this is again 1 by x. Okay, this 1 by x is shifted into logarithm time. We will get the x root, already y is there, so x root multiplying xy root. Here in denominator also 1 by x root is there, x square root. So the above equation becomes LA equivalent to 2 into 10 power minus 7 into, now I am shifting this L1 by x into logarithm. So this numerator term becomes x to y root of d11 dash into d12 dash into so on d1y, okay, into so on dx1 dash into dx2 dash into so on dxy. Okay, the denominator already x is there, again one more x root is there, so x square root of x square root of x square root of d11 into d12 into so on d1x into dx1 into dx2 into so on dxx. Okay, so it will be taken as equation number 3. So this is the inductance of conductor A. Similarly, we can obtain the inductance of conductor B. Let this entire denominator term of logarithm A will be assumed as I have to substitute this 2 into 10 power minus 7 into logarithm of GMD by GMR. Okay, the denominator of this term is GMD and this denominator term is taken as GMR. This GMD and GMR. Okay. Now similarly, if you obtain this equation for conductor B, okay, conductor B, you will get this, that will be taken GMR A, okay, 2 into 10 power minus 7 into logarithm of GMD by GMR B. Okay, will be taken as equation 4 and equation 5. Now this is the inductance value of conductor A. That is 2 into, obtained as 2 into 10 power minus 7 into logarithm of GMD by GMRA, where GMD is the this denominator term of this logarithm and GMR is the this denominator term. Okay, we will discuss later. Now total, okay, if conductors A and B are identical, this implies GMRA which is equivalent to GMRB, okay, which is assumed as a GMR. Okay, if the two conductors A and B are identical, that means both the conductors are having the same substance and equal values. So both the conductors A and B are having equal GMRs. GMR A equivalent to GMR B equivalent to GMR. Therefore, loop inductance of this composite conductor L equivalent to LA plus LB, which is equivalent to 2 into 10 power minus 7 into logarithm of GMD by GMRA plus logarithm of GMD by GMRB. Okay, this is the general loop inductance. If these are identical, we have substitute GMRA equal to GMRB equal to GMR. So this loop inductance becomes 2 into 2. We will get finally 4 into 10 power minus 7 into logarithm of GMD by GMR. This is the final equation of this. This is the final equation of the single phase transmission, two-way transmission line consisting of two conductors. Okay, that will be taken as equation number 7. The units are Henry per meter. Okay, I hope you understand this concept of inductance calculation for a composite single phase transmission system or single phase conductor. Inductance of individual composite conductor is given as 2 into 10 power minus 7 into logarithm of GMD by GMR. Okay. Now we have to go into discuss about what is GMD and what is GMR. Here the GMD is nothing but this equation. Okay, GMD is nothing but we call as geometric mean distance. Okay, geometric mean distance. Simply we can write as GMD, or sometimes we can write as geometric mean distance. Sometimes we can write as GMD. Sometimes we can write as GMD or DM. D suffix M, that is mutual distance. Okay, geometric mean distance. Now geometric mean distance is nothing but it is the geometric mean of distances between conductor A. Each conductor geometric mean distance is nothing but it is a geometric mean of distances of each strand of conductor A to the each strand of conductor B. That is geometric mean distance is nothing but geometric mean distance. Okay, that is GMD is nothing but geometric mean of distances between each and every strands of one conductor to the each and every strands of other conductors. Mathematically, this geometric mean can be represented as, you can calculate it as GMD equal to xy root of, okay, d11 dash into d12 dash into so on d1x, okay, into d21 dash into d22 dash into so on d2x, so on dx1 into dx2 dash, dx1 dash into dx2 dash, so on dxy. Sorry, here it is y, it is y d2y dxy. Okay, If you see this in this previous diagram, conductor A carries one composite conductor carries one conductor 1, 2, 3, so on X. This is conductor A, and conductor B carries some group of conductors, conductor 1 dash, conductor 2 dash, so on, conductor Y. Okay. So this is the geometric mean of distances. That is distance between one conductor to distance between distance between distance between the one strand of conductor A. That is using conductor 1 to conductors, each strand of conductor B, other conductors. Okay, 1 1 dash, 1 2 dash, so 1 Y. Okay, similarly 2 2 dash, similarly distance between 2 to 2 into 1, distance between 2 to 2 dash, distance between 2 to Y, these are so on. Similarly, the distance between strand x to strand 1 dash, strand s to strand 2 dash, on strand x to strand 1. So we have to product of all these distances. Okay, so how many distances we are having? We have taken that truth value. Okay, let us take one example and taken. Okay, for example, for better understanding of GMD, I have taken some example. Okay, we have taken conductor A carries two conductors, conductor B carrying three strands. Okay, that we taken strand 1, strand 2. Okay, otherwise let us choose A, B, and strand B conductors carrying 1, 2, 3. Okay, so the GMD for this example can be calculated as GMD can be calculated as first product of this conductor, each conductor. So there is a distance between conductor A and 1, that's right, that is that D A1 into distance between conductor A and 1, A and 2, sorry, here this one is 2 and this one is conductor 3. Okay, distance between A and 2, DA2, and similarly there is a distance between A and 3, that is DA3, into product of distance between. Now all this conductor A is linked with this distances. Now conductor B21, there is a one distance, so that DB1, the distance between DB2 is B22, this DB2, and next one is finally distance between this B strand to strand 3, DB3. So we are having total 1 2 3 4 5 6, so we will have the total 6th root. Okay, 6th root of this case. Otherwise, if you observe this case, here how many strands are there? 2, that is x equivalent to 2. Here how many strands are existing in conductor T? That is 3, 1 2 3, that is y equivalent to 3. So xy roots, that is x into y is 2 into 3, will get the 6. This is the way we have to calculate the geometric mean distance. Okay. Now we will discuss about the geometric mean radius. Geometric mean radius. Okay, we can simply written as GMR, or sometimes it is called as self distance, or sometimes it is called as self GMD. Okay, we can refer geometric mean radius is referred as simply GMR or DS, that is self distance. Okay, self diameter or self GMD. Now, in the case of GMD, this is a geometrical mean of distances of between each conductor of one conductor to the each strand of another conductor. Okay, whereas GMR is the geometrical mean of distances of each strand of one conductor to the all other conductors of the same conductor only. Okay, so here we are calculating the distances between only one composite conductor only. Okay, for example, I am assuming the conductor 1, conductor 2, conductor 3, so on, conductor X. So here we can mathematically that expression can be written as GMR equivalent to x square root of d11 into d12 into so on d1x, okay, into d21 into d22 into so on d2x so on. So on the products dx1 into dx2 into so on dxx. So this is the mathematical expression of geometric mean radius. That is, geometrical mean radius is nothing but it is the geometric mean of distances between each strand of one conductor to the other conductors of the same conductor. Okay, other strands of the same conductor. Let me solve this with one example. Okay, I have taken one conductor A which is having a three conductors. Okay, so I have taken conductor A having two conductors. Sorry, here this one is x square root. Okay, two conductors, labeling conductor A and conductor B. Okay, now here the GMR can be calculated as, now first A to A, there is a distance between A to A, that is the self distance DAA, and next one is DA to B. Okay, the distance between A to B into distance between of B to B. Okay, distance between B to B and distance between B to A. DA, that I am taken DAA is the distance of A to A, that is self distance of conductor A, and DA will be the distance between conductor A and B. Okay, and next one is DBA. DBB is the distance between conductor B to B, that is self distance of B. DBA. So total we have 1, 2, 3, 4. 4 conductors. We will consider the 4 conductors. Okay. Otherwise, how many conductors we are having in this case is 2, right? So x equal into 2, that is x square root. That means nothing but 2 square 4. Okay. This is the concept of GMD. I hope you understand this concept, understand this lecture. That is flux linkages, how to calculate the flux linkage of one conductor in a group of conductors, and calculation of inductance of a composite conductor, and the concept of GMD and GMR. Okay. In the next lecture, we will going to discuss about the calculation of inductance for a three-phase system. So, thank you.